Boy, that's already a lot better. I'm tempted to leave it right here. Boy, that's already a lot better. I'm tempted to leave it right here. Boy, that's already a lot better. I'm tempted to leave it right here. Boy, that's already a lot better. I'm tempted to leave it right here. Hello, Internet. My name is Quinn, and this is Blondihacks. I've had that milling machine for about a year now, and I've enjoyed it very much. Everything that I said in the review of it when I first installed that thing is still true, including some of the negatives. And one of the negatives with that machine since day one has been the fine feed on the quill. It's janky and doesn't work very well, and it's got some really cheap components in it that I want to address, and we're going to fix all of that right now. Allow me to begin by demonstrating the problem. Partway through the travel on the fine feed on the quill on this mill, you can see that sometimes it slips, which is pretty terrible. And then further down, it starts to get into these tight spots. Roughly every inch or so of travel on the quill, this fine feed gets very, very tight. And you can still use it, and I've been using it for the past year since I've had this machine, but it is extremely annoying if that tight spot happens to occur at a critical moment when you're trying to set a very specific dimension. Here's the shaft that runs back from that knob through the casting. Because the problem is cyclical, that certainly seems like probably a bent shaft. That's what this feels like. So I suspected that this shaft here might be the problem. Although it does look okay, so I think we're going to have to investigate further. The slipping problem is new, and that's no doubt something wrong with the clutch. You can see that the fine feed is free spinning normally, but then you can tighten this knob to engage the fine feed clutch mechanism. And that used to work just fine, but recently has started slipping and it's been getting worse. So there's something wrong in there that will also definitely need investigation. Conveniently, the machine comes with an exploded parts diagram in the manual, so I can see how to pull it all apart. This is an exercise in value engineering, so unsurprisingly, there's not much to this system. I have hated this fine feed knob since day one. It's chintzy plastic. Wait, no it isn't. Look at that. This thing is actually a cast aluminum knob that's even been machined on a couple of faces. This is quite perplexing because I really thought this was a cheap plastic knob. In fact, it's cast aluminum and they've put some kind of plastic coating or overmolding on it that makes it look and feel cheaper than it actually is, which is odd. Curiously, there's even a hole in the casting for what looks like a crank handle. So this is probably a part from something else that they've repurposed. That's pretty common in discount machinery. And then they've also riveted this tin plate on the front, which makes it look even cheaper still. I'll start by removing the quill and clutch mechanism. The clutch knob simply unscrews and the whole quill comes off. That's nice and simple. Inside here we have the clutch return spring. That keeps the thing disconnected when you're not using it. It's a very simple setup here. These parts are actually all quite nicely made. Nothing wrong with those. I'll remove this trim ring next. Amusingly, this trim ring actually turns out to be the outer bearing that the quill shaft is riding in. So once again, value engineering there. Make every part do 7 things. Looks like the quill shaft should just pull out now. I've got a cushion under the quill just in case the quill drops. I don't think this shaft should be retaining the quill, but just in case. There it is, all covered in a mix of grease and oil. Not sure what it's supposed to have on it, but it has both. And then this sliding clutch collar here is the actual clutch mechanism for the fine feed. I'd like to remove this clutch collar, but it won't slide over that key slot because that slot has not been deburred. That's the other way they save money on discount machinery. They don't deburr anything because that is labor. Labor is expensive. So I will deburr it before pushing that collar off so I don't chew it up in the process. Looks like from the parts diagram, I'm going to have to remove this set screw on the side in order to pull the fine feed shaft out. It's apparently being held in by this set screw and nothing else, so that should be easy to pull out. But nope, still won't come out. Aha, second set screw. If you've taken apart a machine tool or two, you know that they often stack set screws as kind of a locking nut sort of situation. This is not something I've seen in cars, which is where my mechanical aptitude generally comes from, but machine tools do it a lot. There's a dog point on that one, so that's probably retaining in a groove on the shaft. Indeed, that was the ticket. Out comes the worm drive for the fine feed. Now let's get all these parts cleaned up on the bench and have a look at them, see if we can see what's wrong. I don't see any obvious damage on anything off the top. The wear pattern on the teeth on the quill looks perfectly normal. Nothing out of the ordinary there for a year of use. The clutch collar looks very good indeed. No signs of wear or damage or anything wrong with that at all. In fact, these parts actually look very nicely made, kind of surprisingly so, especially this worm gear. It's very nice. The end of it needs deburring, which I did, but otherwise I don't see anything wrong with it. Now, I suspected one or both of these shafts is bent, so let's do some inspection on them and see if that's the case. Well, the worm shaft is not awesome. It's got 0.07 of runout in it, so there's definitely something not ideal here. The runout is about the same at both ends, so this might be bent, or it might just be poorly made. If it is bent, that would certainly explain our problem, so let's put a straight edge up here and take a look. I really couldn't find anything wrong with it on the straight edge with a light. I also ran it on my surface plate and couldn't find anything wrong there, so if it is bent, it's not bent very obviously. A fairly large bend would show up with this method. However, let's try something more accurate. So I've marked the high spot on the shaft, and running the dial test indicator down it, however, the runout on the shaft all along one axis on the high spot is the same, which is not what you would see if the shaft was bent. There would be a high spot somewhere in the middle of the shaft, and then the runout would get less at the ends, or rather the runout would shift at the ends. But that's not what I see, so it does not appear to be bent. The runout could also be explained if the shaft wasn't round, so I took some measurements down the length 90 degrees apart, but the roundness of the shaft is actually excellent, like really excellent. It's less than 1/10 out of round anywhere on the shaft that I measured, so that's definitely not the problem. Checking the other shaft now, it's a similar story. It's running out less. It's running out about 0.05, but again, the runout is consistent all the way down the shaft, and measuring laterally along one axis, there is no bend detectable in the shaft. It's just that the entire shaft has about 0.05 of runout in it, similar to the other one. Now the clutch collar is extremely nicely made. It's got less than 0.5 of runout on it, and that's including the running clearance on the shaft below it. Even the gear teeth themselves, measuring the high points of those are all within 0.5. Again, most of that's probably in the running clearance on the shaft below. So the clutch collar is extremely well made. Maybe the problem then is in the mesh of the two gears. So I've got some Prussian blue, and I'll smear up the worm gear and we'll check that. Since the shafts both have runout in them, the gears might not be meshing very well, even though the shafts are both straight. So I ran the whole system through its paces, make sure I got all the contact surfaces on both gears, run through a couple of times, and honestly, I don't see anything wrong with that. The contact pattern on the gear teeth looks just fine. When I was doing that, however, I noticed something about the problem. As I was running it through its paces, I marked the tight spot on the clutch collar, and I noticed that it's always tight in the same area of the clutch collar. There's about an 80-degree window where it gets tight. I marked the beginning and end of where the tightness is on this clutch collar with some Sharpie mark, and it's extremely consistent. As I do one full lap of the clutch collar, it always gets tight in that same spot, which would seem to point to a problem with the collar or the quill shaft. However, I noticed something else while I was doing this. The tightness doesn't start until the fine feed knob is in a specific range of its travel. So because it's a worm drive, the fine feed knob moves several rotations for every couple of teeth on the drive shaft of the clutch collar. The tightness only occurs when the 80-degree arc of the clutch collar aligns with a specific 20-degree arc on the fine feed. That's super interesting. That means my problem is not cyclical, it's epicyclical. It only happens when the two shafts are in a specific relationship to each other. That suggests that the problem occurs when the runout on the two shafts aligns in a bad way. 0.05 or 0.08 of runout in either one shaft is not really enough to cause this degree of problem. There's more tolerance than that in the gear meshing. However, 0.13 when the two shafts line up badly could definitely cause this. To test that, I put some Dicam on the tight area of the collar and let it dry. This is different than Prussian blue. This is thin and I'm letting it dry. And then I push that gear in right at the tight spot and work it back and forth a little bit to see if the worm gear teeth will scrape the Dicam that's dry off of the teeth. This will tell us if there's an interference issue that wouldn't show up with the Prussian blue. And sure enough, it's scraping the Dicam off the teeth in a couple of areas at the high spot. So this is definitely looking like the problem. Now, even though there's effectively zero runout in this clutch collar, what appears to be happening is it's inheriting the runout of the quill shaft that it's running on, which does have that 0.05 of runout in it. When the fine feed clutch is engaged, the collar and the shaft become one, and so now the clutch collar also has that 0.05 of runout in it. This definitely appears to be the problem. As for what the actual error in those shafts is, it's not clear. The error exists between the centers and the surfaces of the shafts. So my best guess is that they start with ground rod, centerless ground rod, and they put the centers in afterwards, and then the gear teeth and other features are cut from those centers. And the centers on those shafts don't look very good at all. They are quite poorly cut. So whatever cutter or machine the factory appears to be using to cut the centers is worn out or poorly set up. And then when they go and cut the features from those centers, they end up with 5 to 8 thou of run out in them because of the poor quality centers. That's my guess. Now, what to do about it? You might think I could just change the timing of the shafts so the tight spots never interact, but the travel of the quill goes through several full epicycles of these two shafts. So all you can do is move the tight spots around within the travel of the quill, but you can't ever eliminate them doing that. I'm not going to remake these parts. They're really complicated parts, and it would take a couple of weeks to do that. That's a lot of effort. So what I decided to do is just file down the teeth a little bit on the high spots. I went back and forth, filing a little bit off, bluing it up again, filing a little bit off, bluing it up again. I went very slowly, just shaving at most a couple of thou total over the course of about 10 passes off a half dozen of those gear teeth. And that was all it needed. After that, it now runs extremely freely through its entire range. I can't even tell where the tight spot used to be anymore. So I just basically removed the run out that was in the gear teeth created by the poor quality centers that were used for manufacture. A pretty easy fix in the end once I knew what was wrong. I cleaned all the old grease and oil off everything and reassembled it. I put grease on all of the bearings because they're inaccessible after assembly. I put weight oil on the quill gear because that is accessible, and then put it all back together. The cool thing is once I had it apart, I now understand how the clutch mechanism works. The taper on the end of that collar is the actual clutch. There's a matching taper inside the quill handle. So when I tighten that knob down, it's just pushing those two tapers together. So the slipping problem that it had was just a little bit of oil that got onto the taper. That's what's great about taking things apart. Once you understand how they work, then when problems arise, it's usually pretty easy to understand what's wrong. In this case, until I had taken this apart, the clutch mechanism was a mystery to me. I didn't understand how it worked, and I was worried that problem was going to be much more serious than it is. Well, we've come this far. Why stop making it better? I really hate that not plastic knob, as you know. So I want to replace it with an aluminum knob of my own design. I want to make it bigger, first of all, so I need to figure out how much bigger I can go before it blocks the quill DRO, which would be annoying. That is definitely too big. It's covering up 2 of the numbers. The larger this knob is, the more comfortable it is to use. You get more leverage on the quill spring, and also it's easier to make finer adjustments because of the larger range of motion of the outer diameter of the ring. So I want it as big as possible, and I think I've got a size that'll work. I started taking some measurements off of the knob. Looks like that's a 12mm shaft. I also found this awesome piece of scrap that'll make a great crank wheel. It's already got a dish detail in it that I can incorporate into my design, which I whipped up in CAD. This is sufficiently complicated that it was worth making drawings for, so this is what I came up with. Basically a design that is as big as my paper template was and will fit within the constraints of that piece of scrap that I found and incorporating some of the detail in it. I'll start by making the main crank wheel, and of course this stock is a little bit too small for the large step on my outside jaws, which means I got to use the small step, and thus this becomes the dreaded spinning wings of death setup. I never like working with the chuck in this position, but it is sometimes necessary. I'm going to need to get in deep and machine down a hub on the back of this crank, so I'm going to try and do it with this setup here, just checking my clearances before I do this for realsies. And it's close, but I can do it. Yeah, spinning wings of death indeed. Nobody said machining is for the faint of heart. This aluminum gets very screechy, so I'm going to go ahead and switch the lathe to ocean sounds for your benefit. And let's get going. I'll start by cutting the face of this all the way down to the collar that mounts on the shaft on the back of the crank. When doing a very crash-prone setup like this, you just got to be careful. Spend extra time thinking about your movements with the hand wheels. Don't do anything sudden. Don't do anything dramatic. Be deliberate. Be thoughtful with every hand wheel motion, because if, for example, I crank the cross slide a little bit too far back when I'm moving myself clear of the work for the next pass, I could very easily crash into that chuck jaw. And muscle memory and habit can make you do that. So you got to think through your muscle memory when doing a setup like this, because this is not something that you normally have to worry about when doing turning. While this long cut is running, I'll take a quick sidebar and talk about the general idea behind value engineering in discount Asian machine tools. Let me say up front that Asian import machine tools are frankly a revolution for hobby machinists and model engineers. They have given us a range of machines and a set of features and a quality of machine that was just not available at all through much of the history of hobby machining, and certainly not available at this price point. If you're in the midst of furiously composing a comment about the quality of Asian import tools versus a 1965 Bridgeport, rest assured I've heard that opinion. It's unoriginal and uninteresting, and irrelevant to 95% of hobbyists who have neither the space nor access to such machinery. These machines are built to a price point, and quite frankly, for what these machines cost, they are surprisingly well built for the most part. Correcting for inflation, I've done a whole video on this, a 1965 Bridgeport costs $15,000, so a $3,000 mill like this one, with all of the features that it has and the build quality that they managed to achieve, is actually pretty danged impressive. So for that price point though, you get a few little quirks like we're fixing here today. There, I've saved you typing that comment, and I've saved me deleting it. With that boss roughed in on the back, I then went to this highly extended tool arrangement in order to turn the diameter, get a nice finish, and bring it down to final dimension. Then I did a final fine facing cut, once again in the spinning wings of death dodging setup. Never a dull moment in the machine shop. So far so good. Now I need to drill and bore for the shaft in the back. If you're wondering, by the way, this is 2024 aluminum, which does turn nicer than 6061. It will break a chip if you get the speeds and feeds just right, unlike 6061, but it's still difficult. Not my favorite thing to machine, that's for sure. You know you nailed the dimension when you can't get the gauge pin in because of the air piston you've created, and then you have trouble getting it out again because of the suction you've created. I wish I could say I always get a fit this good, but I don't. But I'll take it when it happens. Then of course chamfer those edges, because chamfers are what separate us from the animals. That's it for this setup. I might as well take the opportunity to do a quick test and see if I got the bore diameter correct, and indeed I did. Boy, that's already a lot better. I'm tempted to leave it right here. Over to the mill to put the set screw hole in the side now, because I'm going to use it for setup. This is an extremely janky setup with 2 points of contact on a curved thing at the edge of the vice jaw. Not awesome, but good enough for a quick set screw hole. Just to drill and tap, and it's fine. I can't resist trying that now with the set screw, because you can actually turn the shaft now. Boy, that's already a lot better. I'm tempted to leave it right here. I went digging through my scrap bin to find a piece I could turn down to make a mandrel, but ended up finding a piece that's an exact fit in that bore, so how do you like that? I guess I needed a 12mm shaft for something, so we'll just use this as is. I'll transfer punch the set screw hole into that mandrel so I know where to put it. And then I'll go over to the mill and drill that out. Here's an old-timer's trick for getting centered on a shaft approximately. Pin a scale to the part with something sharp and then get down low and move the part back and forth until the scale is horizontal. And that'll get you centered on a round piece to within about 5 thousandths, which for most things is good enough. Then I use my pointer to set the X position based on my transfer punch mark so that I land on the right horizontal area of the shaft, and then I'll drill that out. The purpose of this blind hole is so that the set screw can go in and act as a drive pin and not just rely on friction for turning the part. That will allow me to take much heavier cuts, which we'll need to do. This is a fairly large diameter part, so this will be a much better drive. Back to the lathe then, and I dial in my mandrel, and I can get the piece on there and start turning it down. My original plan actually for this, if you're curious, here's another way to do it, was to take an oversized piece, drill the hole in it for the set screw, and then put it in the 3-jaw and turn it down to final diameter. By doing that, you don't have to dial anything in because you've turned the mandrel in situ, so it's guaranteed to be concentric with the lathe, and you can use the 3-jaw. That can be a much quicker method depending on what material you have on hand and how much turning you have to do and so on. But since we already had a mandrel that was the exact size, it was going to be less work for me in this case to just dial it in and use it as is. With that turned down to diameter, then I can face it down to final thickness. You can see that the dish shape feature that was already in the scrap is running out, of course, because there's no reason it wouldn't. It wasn't turned in this setup. So I'll come in with a round nose profiling tool now and do a facing cut all the way to the outsides and true up those chamfer features so that they look nice. I want to fillet these corners now for comfort. I've got a trick for this I learned from Adam Booth. You take a corner rounding end mill with a flat spot on it for a tool holder and a V-groove tool holder on your tool post. Put the set screw down in the flat spot. Presto, you've got a corner rounding tool. Of course, you got to be sure to get the cutting edge on center. If you have a router for woodworking, you can also do this trick with carbide router bits, which are a whole lot cheaper than corner rounding end mills. So if you have those around, give them a try. For the inside now, I have to run the lathe in reverse because of course the cutting edge is facing downward, but no big deal. And a little touch up with the file because when corner rounding with a tool, the tangents of the curves never perfectly line up with the other faces. At least not when I do it. And it should be a really nice comfortable hand wheel now. That is definitely looking good. We're done with the lathe now for this piece, so I'll take it out and take it back over to the mill for, well, let's give it one more test drive while we're at it. Oh, that's nice and doesn't block the DRO. Boy, that's already a lot better. I'm tempted to leave it right here. I think I nailed the size. You can see how much larger it is than the factory knob, and it's not interfering with anything on the DRO. So that is a big win. Now I set it up thusly to drill and tap for the crank handle. Back to the lathe now with a piece of drill rod to make the crank pin in the center of the handle. This is drilled and tapped M4 at one end for the little screw that's going to retain the spinner handle. And then the other end is tapped M6 to go into the crank wheel that we just made. Then I grabbed a piece of brass to make the spinner handle with. I start by turning this all the way down to the largest diameter, which is the large end of the taper on this handle. I made it tapered because tapers always make handles more comfortable to use, and it also looks nice. Then I drilled out the center to be a reasonably free-running fit, few thou of clearance on the crank pin. You don't need this to be too tight. You want it to run smoothly even if there's like a little bit of grit under it or something like that. Then the top of it gets counterbored for the head of the screw that will retain the handle. Then I flip my compound around to 3 degrees and cut the taper. The angle of this taper was just determined in CAD by what looked good for a diameter at the small end and the big end, but somewhere around 3 to 5 degrees is usually about right. Next up, we need the tiny little screw that holds it all together. Once again, with another piece of brass, I just turn down a little shoulder for the threads, which are M4. That gets parted off with a certain thickness for the head to match the counterbore, Yahtzee. Then I threaded that into a piece of scrap to hold it. It's a little tricky to hold onto something this small. And then I cut a screwdriver slot through the middle of it with a slitting saw. Conveniently now, it's very easy to remove from the threaded fixture block. There's something very satisfying about making tiny screws. I don't know what it is. All right, we're ready for final assembly now. Everything's going together with thread locker to keep things from unwinding as the crank handle spins. A little bit of light oil under the spinner handle for the vitamins. The top of the crank pin is slightly above the shoulder on the spinner handle so that as the screw is tightened down, it tightens down on the crank pin, but the spinner handle remains loose. It's a very standard construction for spinner handles like this. All right, final test fit. Here goes nothing. Handle goes on, set screw goes in. Survey says, oh, that is very nice. I'm very pleased with that. Boy, that's already a lot better. I'm tempted to leave it right here. Already, you've been at this for 2 days. Of course I'm going to leave it here. The crank handle is nice for moving up quickly. It doesn't work very well going down because you're fighting the quill spring, which gets harder and harder the further down you go due to Hooke's law. So contrary to a couple of hundred commenters on a recent video, it's not going to be useful for boring heads. However, for fine feeding, the larger diameter knob is really much nicer. I can really feel the difference in how accurately I can hit a specific number on that quill DRO without going over. That's going to be really nice. Well, so long, crappy not plastic knob. Not going to need you anymore. You may have noticed a lot of wiggle in this as I'm cranking it, and that's because the bore on the end of the head casting, which is also the bearing for the shaft, is about 5/1000 oversize. I considered putting a bushing in there to fix that, but there isn't enough room for a bushing without also boring it out oversize, or trying to mount a bushing on the front somehow, which would be a lot of extra work. And honestly, I'm not sure I should, because that few thousandths of slop in the bearing at the end might be what's making it all work with the 13th thou of combined runout in those two shafts. That's what you call tolerance engineering. If the yield on your parts is too low, increase the tolerance on all the mating parts until the yields come up. If you can't make it accurately, make it sloppy. And yeah, that seems like it might be annoying, but honestly, when you're using the hand wheel just with your fingers and not cranking, you don't even notice it. It's been a year and I didn't notice that that was that way until now, so I'm not going to bother fixing it. I got to draw the line on this project somewhere. I'm already 3 times longer than I wanted to spend on it, so I'm happy with where this landed. This is going to be a big improvement to this mill. But wait, one last addendum. Just before wrapping up this video, I told Precision Matthews about the problem, and they actually sent me a completely new set of shafts for this entire fine feed mechanism. And as you can see here on the worm shaft, it now no longer has that runout issue. The runout on this shaft is less than 1,000th. And putting this shaft into the mechanism completely solved the problem as well. So I actually left my other shafts in there because just replacing this one was enough. So maybe I wasted 2 hours filing gears. But still, it was an adventure and I learned how this thing works. I hope you enjoyed the process of watching me go through this. And if you want the plans for this crank for your own mill, they'd be easy to adapt. They're over on my Patreon. Speaking of which, thanks to my patrons for making all this happen every week, and I will see you next time.